Hi, I am Marco Joich, and I'm going to be presenting on Mars, which is the modular agent with reflective search for automated AI research. So first, we'll start with the task description. So the task in this paper is automated AI research. Basically, it's ML engineering. So a single task given to the agentic system is basically a competition-style problem for ML engineering. So you can think of the Kaggle ML competitions, as well as the target data set for this competition and some objective, like a passing criteria. So everything that would be given to a human that enrolls in one of these Kaggle competitions. So, given a task like this, the agent must execute a full ML engineering pipeline, which is basically preparing the data set, doing some feature engineering. So both of those are sort of like pre-processing. Then they need to train and validate models, run the inference scripts to get your final evaluation, final metrics, and then prepare a final submission, which is basically a big file according to some standard given by the competition problem, which would then be used to evaluate the system. So actually, as you'll see later, preparing this final submission is a very important task, which is not always done correctly. Also, in this specific paper, they have limited compute constraints. It's mainly a time bottleneck, but also they do have a specific test suite with a certain amount of GPUs available, and this is all that the model gets to work with. So, like I said before, think of it as just an agent being dropped inside of a Kaggle competition. So the system that they propose is a modular, search-based, and reflective multi-agent framework. So unpacking that, modular means we don't want to just output a single chunk of code, one big file. We want to break our task down into separate parts and then also engineer a repository which accordingly reflects our decomposition of the problem. And then search-based is basically referencing this Monte Carlo tree search, which they use to guide the exploration of this decomposition. So you can think of like them searching in the space of all possible decompositions of their task. And then their reflective memory is basically every time they try something new, they extract lessons learned from this attempt, basically what worked and what didn't. And then when they're creating new ideas, they're comparing the lessons that they've learned from different attempts, uh, potentially reusing information or guiding the generation of new ideas. And also the big thing is that this Monte Carlo tree search is budget aware. So as you know, Monte Carlo tree search is a form of a heuristic guided search, which has a trade-off from some heuristic and also exploring new parts of the search space. So the heuristic here is highly integrated with the actual execution time. It's sort of a trade-off between performance gains and losses in execution time. All right, so now onto the human agent environment architecture. So here's a diagram of the architecture that they put in their paper. So as you see here on the left, our problem is an instruction, the coding environment, and the objective at hand. Then this goes through some task preparation, which is basically exploring the data set. And then it gets plunged into this MCTS guided exploration of the solution space. So whenever you descend through this MCTS tree, whenever you have a space where there's some sort of error to debug, you go into a different branch, extracting lessons, and then obviously doing the actual debugging. You can also kill parts of the search space if they're simply not working. And then when you enter an area of the search space, which is good, which is working, you also have the option to improve on these solutions. And as I mentioned before, this Monte Carlo tree search is guided by an efficiency-based reward, which is a balance between the evaluation score and the cost of that solution. Uh, and so at any point where you're improving, basically branching through the MCTS, you have a system of proposing an idea with one agent, breaking it down with another agent, and then implementing it with a third agent. Uh, and this is all managing this global repository that the agent is working in. And then your final highest score, according to your MCTS tree, is then pushed to the final repository, formatted, and submitted. So now going a bit more, I guess, structured to this analysis. So how does our agent actually situate itself with respect to humans, environments, tools, and policy? Well, humans are basically out of the loop here. We have this big set of like 75 different Kaggle tasks, which were created by humans, but they're not actually present in the task. They've basically created the benchmark, but that's it. So I would say that the humans are out of the loop here. Then the tools available, well, the agent is given some tools which allow it to sort of explore its current environment, like its repository. These tools come in the form of libraries that enable specific engineering tasks and also just the basic I/O to like deal with creating a file, editing it, and running it. Um, so you can sort of think of the environment here then as latent because the tools are sort of the environment, like the repo being constructed is the environment, but at a higher level, the environment is basically the current state of progress of the repository itself. The agent is in a closed loop. It was exposed initially to some input data, and then it has the files that it's created and also this runtime environment, like whatever Python is engine is given to it and the libraries that are given. So sort of what I'm getting at here is that the tools and the environment are sort of like very interleaved here, based on the way that they created this whole ML engineering data set in the first place. It's sort of the case for all of their baselines as well. Now, here's where they diverge from the other baselines is in the policies, planner, and memory. So one thing that I thought was great here is that the planner is basically this Monte Carlo tree search, and then also the idea proposing agent. Uh, but yeah, basically the planning workload is largely pushed to the Monte Carlo tree search over the set of candidate approaches to solving problems or their subproblems. Then the policy also here is it's a lot different than TauBench really. The policy here is if there is a policy, it's basically the heuristic that's guiding the Monte Carlo tree search. So it's this overarching policy of we want solutions that are better, but not at a cost of too much runtime with respect to the improvements of the new solution. Then the memory here is this structured lesson pool, which sort of follows the structure of the Monte Carlo search tree. And these are the lessons extracted of what was the approach, what was the result, and why was the result different here. Then the interactions with these four different things. One thing that is really important to note here compared to some of the other benchmarks that we've talked about is that this environment is very strictly episodic, which is very different than TauBench. Like you don't have any sort of external factors that are sort of shifting the environment. Everything is within control of the agent. Well, I guess it's not strictly episodic, but it's more so that the agent doesn't have any sort of competing force in the environment that will uh, sort of potentially work against it or something that it must collaborate with. So then the interactions with humans, basically, like I mentioned before, the humans only interact by creating the benchmark. And so the agent doesn't ever directly interact with the human. Then the interactions with the environments, well, the three agents together that I mentioned in this slide, idea agent, modular agent, coding agent, they can read data sets, local files, the results of code executions, the scores on the validation sets, the resource constraints that are given to them at the time of the problem, the formatting requirements for their submissions, and also this pool of memory. Uh, then of these, the agents can generate to the environment by writing or running code, local files, code execution results, the validation scores, and the memory pool, as well as the final submission, which I would consider to be a local file. Then the interactions with tools, well, they have this local software development environment where the agent can inspect data, run code, write files, actually train models, which is basically running code within a Python environment, validate those models, which again is running code, and then generating the final submission. So it's basically like if you dropped me into a Linux server and gave me a GitHub repo, those are the tools available to the agent. Um, then the interactions with policies, planners, and memory. So the MCTS is basically created by the idea proposer and the modular agent, which sort of dictate the branching of the Monte Carlo tree search. And then that tree search itself guides which parts of this search space the coder should execute, basically getting a value for the reward at that point in time. Uh, so that MCTS is a very critical interaction here. Then the policy is very ingrained in the planner. The planner should prioritize the speed of the execution as a heuristic for the Monte Carlo tree search. It's not a very strict policy like in some of the soft benchmarks where it's really about human interaction. Um, then also we have memory in this pool of stored experiences, which guides ideas, the modular decomposition, and the code creation. And like I mentioned before, this memory is also like dynamically created by the by this Mars system as it analyzes every single execution that it runs. So, as far as concrete examples go, unfortunately, they don't give us any trajectories, but they do give a broad overview of the flow of the system. So basically, this ML engineering task is formulated as a tuple of a description of the task, the data set, and the evaluation metric, sort of like we mentioned before. The agent first does a task preparation where it uses the available tools for inspecting the data to process the data, creating metadata descriptors for the data set, which it caches for later use. Then in the main loop, basically we repeat the process of the Monte Carlo tree search selecting a node of the search space to expand. Then the planner chooses between drafting, debugging, and improving based on the current trajectory and the lessons learned. Drafting can also involve decomposing tasks into multiple different files or functions. Uh, and the coding agent will then use the tools that it has to find the target files and update the code. These tools basically just allow it to read files and write to them. And then also it uses another suite of tools to execute code, and then it examines the results and it turns them into lessons that were learned. Uh, Now, like I mentioned, the trajectories are not quite available to us, but they do give us a like final result in the form of they've pasted the files from the repo into the appendix. These are very big Python files, so I can't really include meaningful screenshots of them. But we can sort of look at the overarching result that was produced by an agent on a task. So one of the tasks that they mentioned was the classification of toxic comments. The final repo included a file for processing the data, a file where they defined all of their neural networks that were created, a training engine, and then also a utils file, basically a bunch of helper methods. So as you can see there, like this is like a good decomposition that the model has created, which gives a lot of advantages as over just creating everything in one big Python file because it sort of abstracts various different critical components of the overall project into different files. So then moving on to what we actually expect out of these agents. Well, this agent should behave just like an ML engineer trying to solve a problem. That's basically what the benchmark is. Uh, so the agent should understand the task and also inspecting the data, which is sort of ingrained there. It should be able to propose ideas to model the problem. And by modeling, we mean like we're literally like learning machine learning models to solve the problem. then it should build a modular repository. Basically, it should build an abstraction over different parts of the problem and implement those things separately. Uh, then it should also train and validate the models that it creates. And also, it should have an iterative improvement over the valid solutions until there's no further reasonable improvement given the computational limit, which is also managed by the agent. And then at the very end, it should submit a file that is ready for review in a very specific format, just like you would in a Kaggle competition. And like I mentioned before, this is an important part of the problem, I guess. It's not actually something that is perfect from these models. They do mess up here. Uh, so the expected output is basically an optimal solution to the given problem, given the time constraints, and also given the objective that was provided as an input. Um, Now onto the evaluation criteria. So the agents are evaluated on end-to-end ML engineering problems, basically meaning I give you a problem on one end and I want to evaluate your solution on the other end. And we treat this agentic system like a black box. Uh, there were 75 different competitions with tasks in data preparation, model engineering, experimentation, and submission generation. So the agent is judged by the quality of its final submission on the held out evaluation split. So the benchmark also contains different grading scripts for each problem. So this is sort of the evaluation is sort of abstracted to the benchmark itself, which existed before this Mars system was implemented. It's a very common ML engineering benchmark. The testing splits are reconstructed from public data because Kaggle does not make these testing splits public. But again, this is sort of part of the overarching benchmark that they used. The Mars system also slightly augments the testing suite, like on their own sort of benchmark that they ran, to be resource aware by assigning points for solutions that are more optimal resource wise, or more so killing solutions that are below a certain resource limit. So the main benchmark that they used was MLE Bench, which is built from 75 different Kaggle competitions. And it benchmarks the ability to solve any arbitrary ML engineering problem. So the task level metric comes from Kaggle as it is defined in the original competition and then just sort of inherited by the MLE bench. And then the performance is interpreted based on leaderboard thresholds compared to human submissions. That means were you above the median and were you above different thresholds to get a medal in the competition. Now onto the baselines. So there were four sets of baselines here. Well, I guess as I grouped them, there were four sets. So we have leaderboard results, which basically were just pulled from the internet. We have other agents that were ran in the Mars test suite. So this is basically accommodating the resource constraint. And then there were also changes to the Mars framework. So on the leaderboard results, they compared like 5 or 6 agents: ML Master, R&D agent, intern agent, FAMU agent, Lero, and ML Master 2. And these are basically just results that were appropriated by Mars to put in their paper. Then in group 2, they have prior work that was ran on the Mars test suite, which is this AID model, which is an LLM-driven tree search over different Python scripts. Also, the Era Dojo, which is a family of agents, a specific environment for those agents, and also an enhanced operator set for those agents, like special tools. Then groups 3 and 4 were different changes to the Mars framework. So as we recall, the Mars contains an idea proposer, a modular decomposer, a coder, a lesson learning pipeline, and also this Monte Carlo tree search itself. So in group 3, we have two baselines. One is removing just the modular decomposer, and 2 is removing the lesson learning pipeline. Then group 4 are changes to the Monte Carlo tree search. So as you remember, the Monte Carlo tree search was based with a time constraint reward. So the first baseline is just the vanilla Monte Carlo tree search without the time constraint. So just guided by the results of the experiments. Then the second baseline is a greedy search through the search space, just going at whatever the most optimal solution is at every point in time. So here's the example of the modular decomposition instruction. They basically just uh, ask the agent to create a modular repository structure to implement any given idea, but not going into the code. And they give some requirements for the modular system. Then the lesson learning instruction. Uh, so again, it's basically you give the current best solution and the new solution, as well as the results, and you ask the system to analyze and distill a high value lesson learned. So results against the baselines for groups 1 and 2, which were basically prior leaderboard results and then also prior results with a time constraint. As we see here, even with the time constraints, the Mars system has the state-of-the-art results on valid submissions, the above median score, so average tasks that were above median, the number of gold scores, and also the number of scores that gave any medal at all. And this is really interesting that actually a lot of these systems are not even able to give a valid submission in the first place. Mars is the only system that was actually able to do it in all of the test cases. And also, uh, it's sort of interesting that they don't have improvements over bronze scores or silver scores against all benchmarks, but they do have improvements for any medal across all benchmarks. Uh, and also, it's great that they are the highest scoring model in terms of just overall solution quality above median and also having the best number of gold submissions. Uh, then comparing against the group 3 baseline, which was removing different components of the Mars system, they basically they have two axes on these chart. They're comparing on the y-axis the rate of getting any medal, and then on the x-axis, they're comparing the amount of time allotted to a solution. So as you can see, if you remove the lesson learning, you have a pretty big drop. If you remove modular decomposition, you have a pretty big drop. If you remove the lesson learning, you have a huge drop in accuracy, or rather any medal rate. So this lesson learning seemed very, very important, and we'll go into a bit more detail about that later. Uh, so then group 4 is the same evaluation, but with different augments to the Monte Carlo tree search. And as you see, the greedy search performs the worst. Vanilla Monte Carlo tree search is pretty good, but the budget-aware MCTS is what's best. So onto the challenges and error cases. So the first challenge that they have identified here is that evaluation for an ML engineering benchmark is extremely resource heavy. A single problems candidate solution, just evaluating is this candidate any good, can require hours of training time. So like the actual process of benchmarking, even a single task can take a very, very long time if you're not trying to do it in one shot. Also, there is a high architectural complexity associated with ML engineering tasks. And so this basically makes it so that if you're trying to make a monolithic system where you aren't doing task decomposition, you are not going to succeed because the task is too complex and you end up with a jumbled mess of code. They solve this by decomposing tasks. Uh, then also they have this like two sort of open problems, which I don't think that they have completely fixed due to their results, but they've also definitely made some good steps in the right direction. One is opaque credit assignment. So basically, when one experiment works but another doesn't, it's unclear what actually caused the gain. They do have this reflective comparative memory, which helps with the issue. But again, we haven't actually fixed the problem of truly knowing what caused the gain. You just have some guess that an LLM has given you. So who knows, really? Um, really to say something like this improved over this, you require a lot more experimentation, which they haven't actually done in their system. So then there's also long horizon exploration, which they've made a big step towards fixing. which is basically if you're going to try and fail many, many times when doing this ML engineering task, you're going to create this big chunk of context of all the code, all the results, and that's going to cause a big drop off in performance as you get closer and closer and eventually exceeding the context window. So instead, much of this complexity is just pushed into the Monte Carlo tree search. The structure captures basically this whole non-deterministic trajectory of ideas of different decompositions. Uh, and also this like not only it reduces the context size of any given branch, it also retains this branching, this knowledge of potential branching of earlier parts of the trajectory. And then the remaining complexity is further minimized by instead of keeping the entire trace of a given experiment, you're just extracting the lessons that you learned from it and storing it in some structured memory. Uh, so then some of the key error cases to demonstrate these points. One thing I'd like to note is that the paper did not do a very good job of providing a proper error taxonomy. The exact challenges were also not very well outlined, and the taxonomy and the failing trajectories were largely non-existent. They didn't actually give any failing trajectories, which I don't fault them for due to the way that this MCTS actually works. It would be very hard for them to put this cleanly in the appendix, but they should have done an error taxonomy, which they didn't. Uh, Anyway, some of the challenges or error cases that I've inferred is some of these cost inefficient improvements where agents tend to prefer a much more expensive solution, even though it's only a little bit better. So you might be 1% better, but you take 10 times longer to run. Now, this is an error case that they note in their baselines, which they have sort of resolved with their use of the Monte Carlo tree search with the runtime considerations. Then also, this is one problem that they do have, which is the runtime execution failure. So this is a planning search that they're implementing. And one of the big failure points of a planning search using something like Monte Carlo tree search uh, is that the same subplan may be explored many times throughout the same search if it's a subplan of other different branches. So occasionally the same failure point will be rediscovered in these different search branches, which can get very expensive if that failure point took you a few hours, right, to evaluate your system, train, evaluate, and then have some sort of failure. If you rediscover this failure, this is taking hours and hours and hours of time. Uh, Now they do sort of help it with their lessons learned, but this is still an issue to be considered. Then also there is this general failure to isolate what helped and what didn't. They didn't really give a concrete example, but in their experiments, they showed that the lesson learning was one of the most important aspects of the Mars framework, which is basically a nod to the fact that this is a key error case of agentic systems on this MLE benchmark, which they have sort of or resolved with their system. Uh, Now, as I said, it is sort of hard to say what is still wrong with their system because they did not point to anything in the paper, but this is about as good as I could do for the error cases and taxonomy. Uh, so anyway, that is everything. Thank you for watching and have a good rest of your day.